I'm Takaaki Nara from the University of Tokyo. First, I would like to thank the organizer for giving me a chance to talk here today. My talk is on method for reconstruction of electrical properties inside human body using MRI. And this is a joint work with my PhD student, Motofumi Fushimi. And as we consider the application of imaging of electrical property inside the human bodies. And why we think this problem is that the electrical property gives us very useful pathological information. For example, some kind of breast tumor exhibits conductivity changes up to a factor of 10. Let's take a look at this table. For example, the malignant tissue's electrical conductivity in mammary is about 7 times as high as that of the normal tissue. And even for the relative permittivity, it's 3 times as high as that of the normal one. So if we can have an image of electrical properties, small tumor cancer that cannot be detected by usual structural image like X-rays CT may be detected by the other modality using electrical properties. This is the motivation of our research. And there are several kinds of modality to take image of the electrical properties, but recently magnetic resonance-based method has attracted attention because it can give us a very high-resolution image. And it's called magnetic resonance electrical property tomography, abbreviated as MREPT. And in this modality, we simply use a usual MRI device. And in this device, we use a birdcage coil looking like this, and which generates the rotating magnetic field inside the human body. Frequency of which is about 128 megahertz. Then the rotating magnetic field is created inside our human body. Then what's measured by this MRI scanner is the magnetic field distribution. So 3D distribution of magnetic field can be measured. And actually, it is a complex quantity, so amplitude as well as phase can be measured. Then what should be reconstructed is electric conductivity and permittivity. So this is our problem. And the governing equation is the time harmonic Maxwell equations. So denoting the electric field by E and magnetic field by H, they satisfy the Faraday's law as well as Ampere's law. And it's here, the coefficient here, omega is the frequency corresponding to 128 megahertz. And mu 0 here is a permeability, which can be assumed to be constant inside as well as outside the body. And in this Ampere's law, we have coefficient here, gamma. This is electrical properties called admittivity, whose real part is electrical conductivity. And in imaginary part, we have permittivity. And J here is the external current which we apply into this birdcage coil. And we add some radiation condition. So our MREPT inverse problem is followed as follows. Given the magnetic field denoted by H plus inside the human body, reconstruct the distribution of electrical properties gamma. And we have 2 remarks here. First, Hx as well as Hy both are themselves complex quantity, meaning that the X component and the Y component vibrates with different phase. So they are both are complex quantity. And the second remark is that we can only measure H plus, the complex combination of the X component plus I times Y component of the magnetic field. So this is a problem. Okay. So first, let me introduce a conventional method, which is very rough method, but in our field, this is regarded as a standard method. And since we can only measure the magnetic field and we cannot measure electric field from these simultaneous PDE, we eliminate the electric field to have a relationship between the magnetic field H and unknown electrical property gamma. And here is that one, but this is a nonlinear PDE for gamma. So in the conventional method, we neglect this nonlinear term to have simply this reconstruction formula. That is, gamma can be computed by the ratio of the Laplacian of the measured magnetic field to the magnetic field itself. So this is a very simple reconstruction formula, but we have a large significant errors because we neglect the gradient of gamma. Actually, this is a numerical result. These red domains has a large conductivity compared to the background. And along this curve, this green curve shows the true conductivity. And the blue one represents the reconstructed conductivity by the conventional method, neglecting this term. So we have large error, especially where here, this is the boundary between the normal conductivity value and the abnormal conductivity value. And this is due to we neglect this gradient of gamma. But the original purpose of our problem is that to identify small cancer. So the boundary between the normal conductivity and abnormal conductivity, that boundary is most important. And there, this method produces this large error. So this is a big problem. So the objective of my research is to consider the problem when the gamma conductivity and permittivity varies spatially. And in that case, we will derive an explicit formula, closed formula, reconstruction formula, from the measured magnetic field, H+. So from here, we have two parts. In the first part, we derive a direct formula for the 2D problem. And after that, we extend it to the 3D case. Okay, so let me start with derivation of a direct reconstruction formula. And for that, we make two assumptions. The first one is the Z component of magnetic field is equal to 0. And this is from structure of this birdcage coil that we use in MRI device. And actually, let's take a Z-axis along the body axis. And our body is inserted into this kind of coil named birdcage coil. So it has length long. It is long along the Z-axis. So by applying alternating current into this coil, the generated magnetic field is almost parallel to the XY plane. So from which we can neglect the Z component of magnetic field. So this is the usual assumption from the structure of birdcage coil. So this is from this property analysis of the wave field inside the human body using MRI is very suitable for complex analysis-based method. And second assumption we made is that the derivative of magnetic field with respect to the Z-axis is equal to 0. This means we assume that the electrical property does not change with respect to the Z-axis. So in other words, we consider 2D model first. So we consider this 2D model first and derive a reconstruction formula. And after that, we remove the assumption 2 and propose an iterative algorithm for the 3D case problem. Okay. So first, let us derive d-bar equation from the time harmonic Maxwell equations. So we use a d complex derivative and d-bar operators notations. And H plus is given by this quantity, as I mentioned. And similarly, we define E plus, that is the x component plus I times y component of electric field. Then under the two assumptions we made in the previous slides, the time harmonic Maxwell equation can be written in these two forms. That is, first of all, this is Ampere's law, and this is the Faraday's law. So these two are the first order PDE for the magnetic field and electric field. And actually, Faraday's law can be formulated as D-bar problem. Looking in more detail, here is Ampere's law. And Ampere's law gives us a definition of gamma, electrical property. And actually, this is defined as the ratio of the complex derivative of magnetic field to the z component of electric field. So H plus is given for measurement. So its complex derivative can be numerically computed. However, the z component of the electric field cannot be measured. So in order to represent this unknown electric field inside the human body, let's use the Faraday's law, formulated as a D-bar equation. And for D-bar equation, generalized Cauchy formula holds, as you know well. So let F be in this class, and let omega be a domain bounded by Jordan contour. So in our case, omega is an arbitrary domain, region of interest, arbitrarily taken on the slice of the body. And if F satisfies the D bar equation, D bar F is equal to G, then F at an arbitrary position W, its value, W where W is an arbitrary position inside the ROI, region of interest, omega, can be represented by these integrals. The first term is the contour integral of F along the boundary. And second term is the Cauchy type area integral over the domain omega of G. The right-hand side, this inhomogeneous Cauchy-Riemann equation. So because the Faraday's law is written in this D-bar equation form, therefore, the electric field at an arbitrary position inside the human body can be represented by these integrals. So contour integral of the electric field and the area integral of the measured magnetic field. However, okay, so H plus is the measurement quantity, data, but we cannot measure electric field on the boundary. However, from the Ampere's law, the other Maxwell equation, this quantity, Ez, can be replaced by this quantity. So H plus, again, is measured on the boundary. So if we give the boundary value of the electrical property, gamma, then we can compute electric field at an arbitrary position. So by substituting this electric field into this denominator here, we arrive at the explicit reconstruction formula. So this is the main result of this talk. So given H plus in the region of interest and electrical property value on the boundary, then the admittivity at an arbitrary position inside omega is reconstructed by this form. And it's here, you might wonder, okay, H plus again are the measured quantity. So if we give gamma on the boundary, then we can compute this one. And you might wonder how to give the boundary value of gamma. So we can consider two scenarios for that. The first one is that we take omega as a whole body slice. And in this case, the boundary is the skin surface. So the gamma's value is the conductivity and the permittivity of fat. So by some other method, we measure those values, and then substitute those values into here, then we can compute this one. And second scenario is that we take the region of interest as a more smaller local domain inside which a smaller cancer may exist, but the boundary consists of normal tissues. And in that case, we measure the normal tissue values in some other method and substitute those values into here. Then again, compute this quantity. Okay, so let's move on to numerical simulations. We assume these 3 cylinders are colored red domains that has a higher conductivity value, 1 Siemens per meter, that is twice as large as that of the background conductivity value. And diameters of these 3 domains are 10, 20, and 30 millimeter. And we use a numerical model of birdcage coil. And using an FEM software, we compute the magnetic field. And ρ is this square domain with the side length of 82 millimeter. And we discretize this domain where the pixel size is 1.4 millimeter by 1.4 millimeter. This is the usual spatial resolution of MRI device. And 2 remarks for numerics. First of all, we have to compute the singular integral, Cauchy area integral. But if we take the circle centered at the point W with a radius of epsilon, then it's easy to show that this integral vanishes. So in order to compute this integral, we simply remove a pixel that includes the W. W is a point that we want to compute the gamma value. And second remark is for computation. In our formulation, we need the complex derivative of magnetic field. So in order to compute this value, before that we applied Gaussian filter as well as the Binsky-Goulet filter. That is a second degree polynomial local approximation, because if we add the noise to the forward solution, so because without these smoothing filter, it's very unstable. So we first apply these filters, and after that we substitute those values into here. Okay, so this is the result. This is the result by our proposed method. 3 domains can be well reconstructed. In contrast, by the conventional method, the domains are deformed, but that means the boundary, we have a large errors. Actually, these thick blue domains, the conductivity value is negative. That is impossible physically. And if we add 1% Gaussian noise to the magnetic field, and this is a usual SN ratio and practical device. But even with such a noisy data, our proposed method can reconstruct well. In contrast, the conventional method's result is disastrous, and a small domain cannot be distinguished from the artifact. And it's because in the conventional method, we have to compute the Laplacian of H plus, second derivative. So it's very sensitive to noise. In contrast, our method is based on the generalized Cauchy formula, integral-based method. So the noise added is basically in nature smoothed out, filtered out by computing the integral. That's the other advantage of my method. Okay, and next we conducted phantom experiments. So we made this kind of phantom body which has a domain with higher conductivity compared to the background. And we insert this phantom body into the 3 Tesla MRI. And this is the result. So again, the proposed method will identify the abnormal domain with high conductivity. But by conventional method, a large error at the interface between the true normal and abnormal conductivity value, and it's also sensitive to noise. Okay, so let's finally extend our 2D method to the 3D case. The first assumption is still holds. It's okay. But we have to remove this second assumption. The z derivative of h plus is equal to 0. So in that case, we have to put these three terms that we neglected in the 2D model. So the d-bar equation should be changed in this form. So we have to add the z derivative of E plus electric field into the right-hand side of the d-bar equation. So here is our proposed algorithm, iterative algorithm for 3D case. In the first step, let's neglect this term. Then from the 2D version direct reconstruction formula, we can compute the electrical property gamma. And once gamma value is obtained, we can compute E plus because H plus are measured on each slices. So its z derivative can be computed. So this one can be computed. So its z derivative can be also computed. So let's substitute this value into here and then solve this d-bar equation again by using the generalized Cauchy formula. Then the value of gamma is renewed. So we substitute this value into here and iterate the steps 2 and steps 3 to have a true gamma value in 3D case. And simulations. We have this kind of model which the conductivity value changes with respect to the z-axis. And we observe at two planes here and here. And this is a true conductivity value. At lower plane, we have 3 abnormal conductivity domains. But on the upper plane, the conductivity is homogeneous. And this central column shows the result by the explicit 2D model method. So on the lower plane, we have 3 abnormal domains, but whose conductivity value is lower than the true one. And also on this upper plane, we have some ghost here. But the right column shows the result after applying our iterative algorithm. So the value of the conductivity approaches to the true one, and ghost vanishes. Okay, so here's our concluding remarks. So Cauchy-Riemann equation has long been used for analysis of potential fields, but my message is that the inhomogeneous Cauchy-Riemann equation is suitable for analysis of the dual quantity in time harmonic wave field. And actually, in our case of the 2D time harmonic Maxwell equation, electric field and magnetic field are dual quantity. So they satisfy the d-bar equation. Actually, it's from the Faraday's law, which provides a tool for computation of the unmeasurable electric field from the measurable magnetic field. And this property can be used for reconstruction of the electrical properties. And also, the proposed complex analysis-based method gives a foundation of an iterative algorithm for the 3D MR EPT problem. And this content is included in our paper, this. Okay, this concludes my talk. Thank you for your kind attention.
Any questions so far?
In the 2D problem,
Yes.
you're talking about it, if I understood right, you use some experimental data to use the gamma on the boundary.
Yes.
Why couldn't you use the equation itself as a non approaches the boundary,
Mhm.
then you've got a nonlinear integral equation which you can use the experimental thing as an initial guess and iterate on that to find gamma on the boundary.
I see. Yes, we tried that, but it's not so stable, and it was difficult to estimate the boundary value of gamma.
You have to be careful with how you the boundary when you have the principal value integral,
Mhm.
how you treat it is important.
Yes, yes.
Anyone guarantee a priori that the reconstructed gamma is positive?
Gamma is positive. Gamma is a complex quantity.
Yeah, the real part.
The real part, yes, it's positive. Yeah.
But can one guarantee a priori that it is always positive?
In our algorithm, you mean?
Yeah.
Oh no.
Because analytical property it only makes sense when it's positive, right?
Yes, right. So we can put a constraint for the positivity of gamma, the real part of gamma. Yes.
Yeah, as I understand, you use mixture problem, you measure gamma, you use analytic technique, and you use numerics also. In magnetic field, yeah? You said that boundary value problem for magnetic field is solved by console, yeah?
Yeah.
What is the boundary value problem? Could you outline for magnetic field? Which boundary problem?
Which one?
For magnetic field,
Mhm.
you use numerical solution.
Yes, yes. Mhm.
Which problem?
Oh. Okay. So this original 3D problem, time harmonic Maxwell equations, and we make this birdcage coil model and apply the 128 megahertz apply current, vibrating current into this coil, and compute magnetic field inside the coil. Yes.
What's the last question?
Yeah, so there are MRI modalities that already detect quite small cancers, prostate cancer.
Mm-hmm.
One challenge is that it takes a long time to make a perfusion. How long would one of these imaging runs take?
Time.
Yeah.
Yes, it's a problem. Now it takes 20 minutes or 20 minutes to 30 minutes, so it should be shortened for practical use. Yes, thank you.
So perhaps we can thank both of the speakers, the session speakers again now.
Thank you.